In quantum mechanics, we usually denote a vector like this. So this could be like vector alpha. Similarly, we can kind of denote its dual by writing kind of the reverse of that. So, for example, if we had a vector alpha and a vector beta, we can take the scalar product of the two by just reversing alpha and just multiplying that by beta. But in quantum mechanics, we don't disregard complex values, right? In general, our vectors are going to be complex. So for completeness, I'm going to write that this is equal to beta times alpha conjugate. So that's the complex conjugate of that. Now, what's nice about Dirac notation is that we can call a vector anything we want. So we can even put in vector in here. It doesn't really matter because, well, we just need this kind of structure where we have these two little symbols. Now, in quantum mechanics, we usually denote the state of a quantum system with this little Greek letter called psi. And a necessary condition for the state is what's known as the Born rule. So the scalar product of psi with itself is equal to 1. This is essentially a statement about probability, right? There's a 100% chance that an electron is in the state of itself, right? Now, usually, when we want to represent a vector, we choose an orthonormal basis. So what that kind of means is that if we sum over n the outer product of the two basis the basis vectors that we choose, the basis that we choose, we get the identity operator. Okay. Now this is not a 1. This is the identity operator, but it acts very much like multiplying by 1. And that is because if I have a vector like, say, alpha, and I multiply it by this whole thing, if I bring this into the sum itself, I will simply get alpha back, because this part is actually just going to give me back the components of alpha in the en basis, right? And because the basis vectors are orthogonal, this is essentially going to give me back en with the components. So I can call that an, for example. And this is just going to give me back alpha again. Now in quantum mechanics, the basis that we choose, well, there are many different bases that we can choose. And this might sound a little weird, but we can, not only can we choose like a position basis, but we can also choose a momentum basis or an energy basis to express the quantum state in different ways. And that is because the quantum state can be described in all of these ways. I can describe the state fully in terms of position. I can also describe it fully in terms of momentum or energy. And there are many other ways and many other bases I can choose, but we'll stick with those three for now. Now, in general, I can write that for whatever basis I choose, let me just write this out. For whatever basis I choose, this whole thing will be 1. Now, this might seem a little bit like weird notation. Essentially, what I'm saying is if the basis is discrete, then we use a sum. But in the case of like position, right, the basis isn't exactly discrete. It's like continuous, right? Because there's an uncountable number of different positions that you can have. So for example, if I wanted to write this in terms of position, this equation would kind of look something like this. This equation would look something like this. Now I can use these bases to represent the quantum state in many different ways. So if I use the position basis, this is essentially going to become a function of x comma t, because it also depends on time. But I can also use the momentum basis. And of course, I can also use the energy basis, right? All of these bases are totally valid. And something else that I can do is I can express the Born rule in terms of these bases, right? So this is going to become essentially the complex conjugate of our function. And this is just going to be our normal function. So I can rewrite this like this, right? So, and this equals 1. So this is how I can express the Born rule in terms of the, well, in the position basis. And I can also, of course, use the other bases to express the Born rule in terms of the momentum basis or the energy basis. But what's interesting is, I forgot to mention, this is kind of over all of space. So this is an integral over all space. So what this kind of implies is if this is all equal to 1, then if I integrate over a region of space, then I can get the probability that that particle will be in a particular position. So essentially, what this implies is that this is actually a probability density, right? So I can calculate the probability that an electron will be in some region of space, or the probability that the electron will be within some range of momenta, or the probability that the electron will have some energy by simply integrating or summing over those particular regions. Anyway, so that's about it for this video. In the next video, I'll cover operators in quantum mechanics. But yeah, anyway, that's about it.